Welcome to the deep dive. Today we're tackling what might be the biggest mission in all of modern physics.
Unifying quantum mechanics and general relativity, the Holy Grail.
Exactly. And we've found two, frankly, incredibly radical new frameworks that try to do just that. And what's fascinating is they come at it from this single unified idea.
The stochastic quantum correspondence.
Right. The idea that all the quantum weirdness, it isn't fundamental. It's, an emergent statistical property.
That's the core of it. These papers suggest that underneath all that probabilistic fog, reality might actually be, well, simple, maybe even deterministic.
And they're not just doing this for fun. They're trying to solve two really deep, uncomfortable problems with standard quantum theory. First, the measurement problem.
Yes, the ambiguity over what a measurement even is and why it magically collapses the wave function.
And second, what they call the category problem. Basically, how do we account for everything else, all the non-measurement stuff that's happening all around us all the time?
So, for our deep dive today, we're going to break this down into two parts. First, there's the Barandes framework, which gives us the raw mathematics. It proves quantum reality can be described as something called an indivisible stochastic process.
And then, once we have that abstract math, we pivot.
We pivot to the Welker framework, which offers a physical mechanism, a literal geometric model of reality at the Planck scale that, just happens to generate the exact kind of dynamics the math requires.
It's a perfect marriage of abstract math and physical geometry. So let's start with that math, the part that completely overturns what we think a quantum system even is.
Okay, so the key ingredient here is the indivisible stochastic process. Let's call it an ISP.
ISP, got it.
This new engine is based on, and this is the crazy part, just ordinary classical ideas of probability. And it all plays out in a classical configuration space.
So just a space with things in it, no weirdness there?
None. You can think of this configuration space as the fixed ontological stuff of reality, the things that are fundamentally there.
All right, so if we're using normal probability in a normal space, where does the quantum weirdness come from? How do you get things like entanglement or interference without a wave function?
That is where the word indivisible becomes so powerful. An ISP is a non-Markovian generalization.
Okay, let's break that down. Markovian means?
It means the future only depends on the immediate present. The system has no memory, and almost all textbook stochastic processes are Markovian.
So by calling this non-Markovian or indivisible, you're saying the system's history suddenly matters. The probability of something happening now depends on the entire path it took to get here.
Precisely. The ISP's laws are not decomposable over time. You can't just chop up its evolution into tiny independent moments.
Right.
And that inability to be chopped up, that is the mathematical engine that reproduces interference and entanglement.
So it's non-local, but in time, not space.
Exactly. It's a profound shift. And what's so amazing is that this stochastic quantum correspondence, the SQC, it doesn't just sort of look like quantum mechanics. It reproduces all the empirical features, interference, entanglement, all of it, with quantitative precision.
Wow.
And that leads to this radical conclusion. It demotes our most cherished quantum concepts, the wave function, Hilbert spaces. After a century of dominance, the SQC says they're just convenient mathematical appurtenances.
So a superposition isn't a real physical thing. A cat isn't really both dead and alive.
It's just an artifact of the mathematical tool we chose to use. It's not a description of physical reality.
So Barandes throws out the old complex axioms and replaces them with something clearer. What are the new rules of the game?
They're wonderfully simple. Just three. First, the kinematical axiom. You have a classical configuration space. This is your ontology, your Beebles, the stuff that's real.
Okay.
Second, the epistemic axiom. A standalone, time-dependent probability distribution, PIT. This is the informational content, it's what changes.
And the third?
The dynamical axiom. This is the fundamental law. It's a set of sparse, indivisible transition probabilities that tell you how the state evolves.
What I find so compelling here is how the math itself forces you to be skeptical of the old concepts. The reason we can't trust the wave function is because it's gauge-dependent.
Yes, that's the crucial insight. Quantities in the standard picture, like the Hamiltonian or the wave function itself, are mathematically unstable. They're highly gauge-dependent.
Meaning you can change them without changing the physics you actually observe?
Exactly. The material points to two specific types. The first is called Schur-Hadamard invariance.
Okay.
Think of the matrix that evolves the system through time. This gauge invariance means you can multiply every single entry in that matrix by a random phase, a random rotation in complex space.
And nothing changes.
The observable probabilities stay exactly the same. But the wave function and Hamiltonian, which are built from that matrix, they change completely.
So you have different wave functions describing the exact same physical reality.
Precisely. And the other older one is the Foley-Wuthuizen transformation. This is like changing your entire coordinate system in a time-dependent way.
Right.
And again, the wave function and Hamiltonian transform wildly.
Oh.
So assigning them a direct physical meaning is, well, it's like believing the price of your coffee literally changes because you measured it in euros instead of dollars. It's an artifact of your description, not the thing itself.
That really clarifies the split he makes between Beebles and emergibles.
It does. The Beebles are the real stuff. Random variables represented by diagonal matrices, things like position, a particle is at a location.
And the emergibles.
Those are things like momentum, velocity, spin. They're non-diagonal operators. They aren't fundamental properties. They're emergent patterns, statistical amalgams that only show up when a system interacts with, say, a measuring device. They're real patterns, but they aren't fundamental.
Okay, so the math sets up this deep need for a reality that is deterministic at its core, but also constantly, contingently changing. Now we need the physical picture.
Now we need the geometry.
Let's get into the Tangled Dimensions model, the Welker framework. What does reality actually look like at the Planck scale?
So in the Tangled Dimensions, or TD model, the universe is a discrete lattice, a grid of interconnected cores at the Planck scale. And each core doesn't just have our 3 spatial dimensions.
It has more?
It has 9. 3 spatial, which we see. 3 electrical dimensions and 3 so-called dark dimensions.
Electrical dimensions are as fundamental as space itself. That immediately changes how we think about gravity, right? It's not space-time curvature anymore.
Not at all. In the TD model, gravity is a purely geometric effect. It comes from the overlap volume and the angular inclination of the 3 spatial dimensions. Mass literally causes the spatial dimensions to tilt inward toward a center point.
And the more they tilt, the stronger the gravity.
That's it.
I think the explanation for time dilation that comes out of this is just, it's so intuitive, it's mechanical.
It is. Time flow is literally the update speed of the lattice, the tick rate. And that tick rate is inversely proportional to the overlap volume.
So if you're near a big planet,
the spatial dimensions tilt more, the overlap volume increases, the geometry gets more complex, and it takes longer for the core to run its update cycle. Time itself slows down. That's gravitational redshift, right there in the mechanics of the lattice.
So gravity is really a gradient in the speed of information. Okay, what about the other forces? Electromagnetism.
That comes entirely from the electrical dimensions, the X, A, and Es. An electric field is just the bending of these dimensions toward the core center.
And a magnetic field.
A magnetic field is the twisting, the rotation of those same dimensions around the center.
And that simple rotational idea, it solves the whole magnetic monopole problem, doesn't it?
It does, very elegantly. Because magnetic fields are literally a dimensional twist, they have to form closed loops like a vortex. It's geometrically impossible to have an isolated north or south pole.
And charge quantization.
That also falls right out. Charges are integer counts of little geometric distortions, or kinks, in the electrical dimensions. That's why charge comes in discrete units. Gravity doesn't, but charge does.
And the particles of the standard model are just different combinations of these kinks.
That's the idea. An electron is a core where all 3 electrical dimensions have a specific negative kink. Quarks, like up and down quarks, are just different combinations of positive and negative kinks across those 3 dimensions. Even color charge is just the geometric arrangement of those kinks.
What about the heavier particles, the second and third families, like muons and tassis? In the standard model, they always just feel like weird, heavy copies.
The TD model explains them as dimensional cross-connections, faults, where, say, the X dimension accidentally connects to the wrong end of its neighbor. One cross-connection gives you the second family.
And the third family.
All 3 electrical dimensions are crossed. This increases the geometric complexity and the overlap, which is why those particles are so much more massive and unstable.
Okay, this is it. This is the aha moment. This is where the 2 frameworks connect. The Welker TD model provides the physical reason for the abstract math of the Barandes SQC framework.
Yes.
Barandes needed that random contingent ingredient, that probability PITC. Where does that randomness actually come from in this geometric model?
It comes from inescapable fundamental lattice noise. In the TD model, the contingency is generated by the Planck scale structure itself. It's constantly, for lack of a better word, shaking. There's noise from cosmic background, sure, but the main source is the inherent micro-oscillations of the dimensions at every single core.
It's the physical version of the quantum foam concept.
It's a literal quantum foam. And that's the synthesis. The TD core update dynamics are a physical mechanism for the Barandes epistemic axiom. The probability we observe isn't fundamental weirdness. It's the statistical result of this incredibly complex, continuously vibrating lattice.
So the world is classically determined at the core level, but there are so many variables fluctuating so fast that all we can ever see is the statistical average.
That's the picture.
Let's use this unified model to look at the weirdest particle we know, the neutrino. How does this explain neutrino oscillations?
Okay, so neutrinos are neutral composites. Their weird negative parity is because they have oppositely aligned kinks that cancel out their charge. The key is that their center is unstable.
And their oscillation between the three flavors, electron, muon, tau.
That happens because the quantum foam, that lattice shaking, is constantly putting a little energy into the neutrino center. And this energy can spontaneously create or dissolve those dimensional cross connections we talked about.
So the flavors are just different numbers of crosses.
Exactly. An electron neutrino might have 0 crosses, a muon neutrino 2, a tau 3. The oscillation we see is just the statistical signature of the number of crosses constantly changing because of the lattice noise.
And the weak force, the force behind radioactive decay, also gets a mechanical explanation.
Right. It's not just some abstract gauge boson. The weak force is reinterpreted as the spatial dimensions always trying to get flat to reach equilibrium. In neutron decay, a down quark turns into an up quark. When that happens, the core's spatial dimensions violently relax.
They snap back.
They snap back to a flatter state, and in doing so, they force the quark's kink to invert and eject a transient particle, the W boson, which is just the byproduct of the geometry reconfiguring itself.
So every weak decay is just the universe ironing out its own wrinkles. That's an amazing way to picture it. And this geometric view redefines everything, even something as basic as spin.
Oh, absolutely. Spin is not intrinsic in the TD model, it's emergent. It's a continuous wave of rotational updates circling the particle's core.
A wave.
Yeah, these waves are generated because the electrical dimensions are trying to maintain a kind of spherical symmetry, but they're trapped inside this rigid cubic lattice.
And in the Stern-Gerlach experiment, we only ever see 2 results, spin up, spin down. Why only 2 outcomes from a wave?
That binary result is a feature of the geometric constraint. The rotational axes are confined by the cubic lattice. So when you hit it with an external field, there are only 2 stable low-energy configurations for that rotational wave to precess in. Up and down are just the 2 easiest paths the geometry allows.
Looking at the whole picture then, Tangled Dimensions unifies all 4 forces just through geometry.
It connects them perfectly. Gravity is spatial dimension overlap. Electromagnetism is the bending and twisting of electrical dimensions. The strong force is the quest for equilibrium among the quarks.
And the weak force is the spatial dimensions snapping back to flatness.
It all just clicks into place.
So finally, what about the fundamental constants that define our universe, like the fine structure constant, alpha? We usually just accept its value.
But in TD, it's not arbitrary at all. Alpha emerges as a direct measure of how much the electrical dimensions overlap with our spatial dimensions. Its small value, about 1/137, just means that the interaction, the leakage between the electric and spatial dimensions is limited.
So what we have here at the end of the day is a systematic pivot. We're moving away from abstract, uninterpretable ideas like the wave function.
And toward a concrete deterministic foundation, an underlying configuration space governed by these indivisible stochastic laws.
Which are physically created by a geometric, continuously shaking lattice.
The unified model really reframes how we see everything. The Barandes framework suggests that if you want to keep locality in space, which this model does, you have to pay a price.
And that price is non-locality in time.
The non-Markovian, indivisible nature of the whole process.
And it's that non-locality in time that provides the contingency, the randomness that we see in quantum outcomes. So here's the final thought for you to chew on. If the universe's future depends on its entire past, and that past is encoded in this impossibly complex, shaking lattice of tangled dimensions, what does that really mean for causation? If time itself is just a local, geometry-dependent tick rate, then maybe the chain of cause and effect is far more complex and maybe far more fixed than we ever imagined.